You. Good morning.
Good morning, sir.
Good morning, sir.
Okay. So, so you are unfortunate, or I am unfortunate, or both of us unfortunate. Huh? Because I am unable to give you the notes. I am just dictating, but that by dictating, probably you are unable to understand anything. You are understanding nothing. Okay, because of my laptop problem. It is not my laptop. I think you are looking not my name, you are looking Mustafi's name. So either I am doing class on his favor, or hmm, you should be able to know that I am utilizing his laptop. So in last two class, we had discussed about the slab. We had classified the slab, and there we had designed one the problem I had just dictated here by my mouth. Okay, so that after 1 week you will be able to get it. By 3-4 days my laptop will be clear, then I will be able to copy that is available in my laptop. So one-way slab. So one-way slab means it is having support on two opposite edges, normally on the two longer edges. If this slab is supported on all four edges, in that case also a slab may be one-way slab. So in that case the condition is if longer length to shorter length ratio is greater than 2. In that case, the slab will, although the slab is supported on all four edges, it will be effect will go on with respect to shorter span, and only 5% load will be transferred to the longer span. Okay, so that we had solved the problem. The solution is very simple. Only first few steps are different. After that, it is exactly similar whatever we have done with respect to simply supported beam. Okay, so now today let us hear, I will talk with respect to two-way slab. With respect to two-way slab. And what is two-way slab? So two-way slab, if we want to give the meaning, a two-way slab means effect of load acting on the slab will be transferred in both direction, both longitudinal direction as well as shorter direction. Okay, this is one thing. But in respect of one-way slab, load was always transferred with respect to shorter span. This condition is the other condition that we had already defined, that Ly by Lx, longer span to shorter span ratio. If longer span to shorter span ratio is less than 2, then it will behave as two-way step. See, this definition should count. Now, it is supported on all four edges. It is supported on all four edges. Now, condition is that the slab on all four edges may have continuity. Or the continuity may be with respect to in one direction. The continuity may be in two direction. The continuity may be in three direction. There may the continuity may be in all direction, all four direction. Continuity may be in three direction. Continuity may be in two direction. Okay, so if the continuity is only on one direction, the continuity is only one direction, that means other three direction are having discontinuity. That means discontinuous. Discontinuous only in one continuous. So this is one condition. Now, before going to this, I want to say of two-way slab. For design of two-way slab, you are to follow some rules given by IS 456. Given by IS 456, I told all of you. I told all of you that you are to download. You are to download IS 456 from net, and you are to go to the IS 456. So everything is there. Now, with respect to two-way slab, with respect to two-way slab, the IS 456 gives. You are to remember nothing. You are to remember nothing with respect to your examination. IS code will be permitted. Okay, but you are to remember these things when you are to go appear for competitive examination. Right? Now, since this is available in IS 456, if you are having pen and paper, you will get in IS 456 as Appendix D. As Appendix D. Now, these things you will get in all textbooks, just reprinted. Is represented by capital L suffix Y. Shorter span is this mentioned by shorter span capital L suffix X. So LX and LY. So if LY divided by LX is less than or equal to 2, then it is two-way slab. So if two-way slab, then load distribution, if small w is the intensity of load acting on the slab, some percentage of load will be transferred along shorter span, some percentage of load will be transferred along longer span. Now, load transferred along the shorter span, it is LX, so it is, as per code, it is represented by WX. And load transferred by along longer span, it is WY. Okay, but in the expression whatever given in IS 456, the use of WX and WY is not there. The use of only W is there. That means actual magnitude of load. Now, see if our slab is simply supported on all four edges, as we had obtained in our solution of last problem. In our solution of last problem, our maximum bending moment is WL square by 8. WL square by 8. Now, with respect to two-way slab, the code is given because we will get bending moment with respect to shorter span, as well as we will get bending moment with respect to longer span. So shorter span ratio is designated by MX and longer span ratio is represented by MY. Right? Now this 1 by 8 is replaced here by some factor. So MX is represented by alpha X times W into LX square. My is represented by alpha Y W into Ly square. Now these two expression is available in the code itself in Appendix D at page 90. At page 90, this is written there. You can see it, go through it. It's very simple. Okay. Now where from we'll get alpha X and alpha Y. Now this code represents not only for with respect to simply supported, because if it is simply supported, that means there is single panel of slab. A single panel of slab. That means there is no continuity. But if there is continuity, that means slab is not a continuity. This is not a simple independent panel of slab. It will be a continuous slab. It will be a continuous slab. When it is called continuous, they say you had got in structural analysis continuous beam. Continuous beam. So continuous beam, in continuous beam there should be more than two. More than two. If a structure is there, there are three supports. If there is three support, that means there are two span. Then it's a continuous beam. So minimum there should be two span, or minimum there should be three span. Then in the continuous beam. And continuous beam, and what is fixed beam, what is fixed frame. So in continuous beam, the basic thing is that at the end, moment will induce, at which span moment will induce, but no moment will be transferred to the support. No moment will be transferred to the support. That this is the conception of continuous beam. There is support beam onto this beam. There is maybe column. No moment will be transferred to this. Whatever moment, fixed and moment arises, that will be automatically balanced by the beam itself. So that is the continuous beam. So that is the thing. Now, if continuity is there, then say for a fixed beam, our moment was, if intensity of load is W, L is the span, then at end, all of you had utilized at end, bending moment induces was W L square by 12. And because of this moment, there is a probability of tension on upper side or upper surface of the beam. And that's why this moment is called as negative moment. Conception is that many engineers concept that if on a beam, due to moment, tension is occurring on upper surface, then that moment is designated by sign negative. And the moment that is induced at bottom and tension is at bottom, then that will be positive. Now this moment acting or induced moment near this support is always negative, because tension is occurring at upper surface. So okay, so negative or hugging moment is represented by negative, and sagging moment is represented by positive. So for shorter span, the expression alpha x into W L x squared. This now we can expand minus alpha x times W L x squared plus alpha x W into Lx squared. Negative moment, positive moment. So now where from we will get alpha? Where from we will get alpha? So for getting this alpha in IS 456, there itself at page 91. At page 91, there is a table. At page 91, there is a table. And from that table, at this moment, you will not be able to see, you just record it, the table number 26. The table number 26. From that table, we will be, for different boundary conditions, we will be able to find out plus x, plus alpha x, and minus alpha x. And similar value for alpha y also, from the same table. Now here in that table, there are 9 types of slabs, or there are 9 types of slab panel. That's whatever I told you. The 9 types of panels are: number 1, interior panel. That means with respect to that panel, or that panel have continuity on all four edges. On all four edges. Okay. What else? নাই এতিয়া গুৱাহাটীত শ্বিলঙৰ পৰা আহিল সেইটো টাৰ্ম শেষ হ'ল তেখেতৰ মই SMS কৰি দিম হা মই অলপ পিছত দি আছো না ইমিডিয়েটলি লাগে দাস দাস আপোনাক মানে আধা ঘন্টা পিছত দিলে দেৰি হ'ব নেকি তাৰমানে মই অনলাইন ক্লাছটো কৰি আছো তেতিয়া মই কৰি কিনে আপোনাক দিম মই sorry for the phone call counts. Okay, so in that table you will get so I am just dictating. The second one is one short is discontinuous. There are four edges, two long edge, two short edge. Two long edge, two short edge. So out of that, one short edge may be discontinuous. Similarly, one long edge may be discontinuous. In this way, we will get 9 types of panels, right? And then the values of Ly by Lx are given there. There are 5 conditions are given. Ly by Lx is equal to 1, 1.2, 1.1, 1.2, 1.3, 1.4, 1.5, 1.75, and 2. Then with respect to that, we will be able to find out the value of alpha x, and the last column is with respect to alpha y. Okay, see, first part is same, whether it is, that means load calculation part, the moment calculation. So by this way we will be able to find out moment for shorter span at end and at mid, moment for longer span at end, at mid. Okay, that means for a single panel we are getting 4 bending moment, 3 in longer directions, 3 in shorter direction, in shorter direction. Out of this, unfortunately, the mid span moment acting for either direction is at the same point. So that is the critical point. What is the critical point? But our next procedure is just repetition. We got the moment, then we have to find out the factored moment. After getting factored moment, we have to find out the effective depth required. At the initial stage, we had assumed some overall depth. From overall depth, we calculated one effective depth. Now we are required with respect to moment. What is the effective depth required? So for that, we will always utilize the critical moment conditions. Critical moment condition, mu is equal to 0.138 FCK BD square. Here B is 1 meter. B is 1 meter, so we will be able to find out the effective depth required. Now we have to compare the effective depth that available from our assumption and effective depth that is required. If effective depth available is greater than effective depth required with respect to critical condition, that means the section is safe with respect to single reinforced section. With respect to single reinforced section, then we have to find out the amount of steel. We have to find out the amount of steel. Once we got amount of steel, how to find out the same formula? Mu is equal to AST divided by 0.87 Fy bracket small d available is equal to 0.4 to XU. Now XU we have to calculate. Same expression, whatever we had utilized in beam as well as in slab. XU is equal to bracket 1.2 minus bracket 1.44 minus under root 6.69 mu divided by FCK BD square whole thing bracket multiplied by AT. Now we have to compare the actual neutral axis, actual neutral axis depth and critical neutral axis depth. If actual neutral axis depth is less than critical neutral axis depth, then we are safe. This slab can be designed as under reinforced. But if XU happens to be greater than critical neutral XU maximum, then we will have to go for double reinforced because we cannot go for over reinforced. But slab is normally designed as single reinforced. For our normal construction, for unusual structure, it is something different. For normal structure, our slabs are normally designed with respect to singly reinforced and under reinforced. Singly reinforced and under reinforced. So by this way, we will be able to find out amount of steel required. Then this steel required we had calculated with shorter span. For longer span also we have the moment. For longer span we have moment. Then with respect to and procedure we are able to find out the amount of steel required. Okay, so we calculate the steel required with respect to longer span as well as with respect to shorter span. But we'll have to check it whether whatever amount required is within the limit. That means we have to check minimum amount of steel, whether whatever steel that we had calculated with respect to moment is greater than the minimum amount of steel. For calculating minimum amount of steel, our expression was 0.0012 B into capital D. Out of this, B is 1000, that is 1 meter. D we had already fixed. So this amount of steel will be required minimum. If at all, from moment point of view, it is not required. But if whatever moment or area of steel obtained from our calculation is more than this, then whatever about steel is required that we have to provide. So for this, since it is a slab, normally in slab, the spacing is mentioned. In beam, take care of this. Almost all students made this mistake. For beam, normally number of steel is calculated, and for that is normally given a spacing. So we have to find out the spacing. So formula for spacing I had gave in last solution of problem. So spacing required will be equal to area of the type of rod assumed multiplied by 1000 divided by AST, or we can say spacing required is equal to small as or AS, A suffix S multiplied by 1000 divided by AST, where AS is the cross-sectional area of single rod whichever we are assumed. So from this we will be able to find out the spacing required. Similarly, we will be able to find out the spacing required with respect to longer dimension. Now again, for spacing there is a guidelines, permissible spacing. The spacing that we will be able to utilize, we will have to see. For reinforcement with respect to shorter span, the number one is 3 times effective depth. Number 2, 300. Number 3, whatever spacing required with respect to area of steel. Okay, those spacing to be provided should not be more than smaller of this tree. So we will be able to now fix it. And similarly for reinforcement in longer direction, here only think that one is in place of 3 times effective depth, it is 5 times effective. Others are 300, others are exactly required. So from this, we will be able to fix this spacing required. So from bending moment point of view, up to this, if we can do, then our design completes. Okay, so from strength of point of view, our design completes. Now we have to design with respect to serviceability point of view. So from serviceability point of view means we have to check the deflection. So for checking deflection, the again code is given. The thing I have told in last class. So we have to find out the percentage of steel with respect to shorter span direction. Okay, then into Fy into divided by area of steel provided. We'll get that value. And with respect to this Fs, there is a curve that I show yourself and that I gave at the time of doing our design of beam. At the time itself I gave you. So from that we will be able to find out the modification factor K1. Modification factor with respect to tensile steel K1, and there itself another curve is there. From this we will be able to find out modification factor K2 for compression steel. And since in this slab we are rarely giving compression steel, normally do not require, so K2 is always equal to 1. Okay, this thing's calculation. Now again in code it is given that basic span to depth ratio. These things I gave you in note at the time of design of beam. Basic span to depth ratio is 20. Then maximum span to depth ratio up to which we can go. These things also we have done at the time of design of beam is equal to K1 into K2 into basic span to depth ratio 20. This. Now span to depth ratio, whatever is given, that we have to. Now this span to depth ratio, whatever given, it should be less than span to depth ratio up to which we can. If this condition satisfies, then stability condition satisfies. Okay. Next, one condition is there, the development length. The rods should have development length. So for development length, we had one expression, 0.87 Fy times 5 divided by 4 times tau BD. This tau BD is the bond strength, and in code itself it is there. We are utilized. So from there we will be able to find out tau BD. Then there is a condition given in the code that I had mentioned there. If it is torus steel, then whatever value is given there, we can increase by 60%. So from this, we will be able to find out development length. Now we have to see development length means from maximum bending moment towards the bending moment reducing. So maximum bending moment is at which, and towards the support, the moment is reducing. Now we have to find out what is the length available from midspan to the edge. Be less than whatever length available, whatever length available, then the development condition is safe. So it is just repetition. Only first part is the things. Are you getting? Yes?
Yes.
Then,
Yes, sir.
then if I have to, if I discuss a solution of problem just by mouth, I don't think it will be effective. Or you feel you will get some fruits. Because the scripting thing by mouth and numerical thing by mouth, it is not same thing. Did you got some idea in solution of the last problem? Just I had discussed mouth how calculation is done. Okay. Okay, that solution I will give later. So we had designed beam and we had designed slab. We had designed beam and we had designed slab, right? So the load flow diagram is the load is a load always acts on slab, and from slab the effect of load is transferred to the beam. Is transferred to the beam, and from beam the effect of load is transferred to column. So next chapter will be our design of column. Okay. So today I do not want to start that. Today I do not want to start that chapter. Or should I start? Anyone?
No, sir.
Better not. Did you purchase any textbook? No.
No, sir.
You try to purchase some books. Okay, today I will stop.